Hello and welcome to a new video series where we will talk a lot about so-called Hilbert spaces. Hilbert spaces are an important part of functional analysis and they occur a lot in applications. And for this reason I think it's very helpful to have a whole separate video course about them. And now before we start with the introduction, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And I should tell you, as a supporter, you have access to a lot of additional material, which you can find with the link in the description. For example, for all my video courses, you find quizzes and PDF versions that help you learn the topics. Okay, then let's start here. And first I want to tell you what this video course is about. So essentially, we will just do functional analysis for Hilbert spaces. And now, as you might know, there is already a whole functional analysis course on this channel here. However, only a small part of this course is actually about Hilbert spaces. Therefore, the idea is that we extend this small part here to a full-fledged video course. And indeed, this might be also helpful to understand other video courses here, for example, my course about unbounded operators. So this is a more advanced course where formal knowledge of functional analysis and about Hilbert spaces definitely help. Okay, so this is just a little bit of motivation to see where the course about Hilbert spaces is embedded. However, more important for you is to know what are the prerequisites for this new video series. And there I can tell you, you definitely need knowledge of real analysis and linear algebra. So in fact, it's exactly the same prerequisite as for the functional analysis course as well. However, at this point I can also tell you that my new abstract linear algebra course is also really helpful for understanding Hilbert spaces. Simply because we will generalize a lot of topics from here to infinite dimensions. And I would say it's always helpful to first understand the finite dimensional case. Then, indeed, the infinite dimensional case we cover here is not a big stretch anymore. Okay, then let's talk about the topics we will cover in this video series. Obviously, we will start talking about inner products. And such an inner product on a vector space will give us a geometry, so we can talk about orthogonality as well. And this will lead us to a special form of a basis, which we have in Hilbert spaces. And the most important notion there will be the so-called orthonormal basis. And with the help of such a special basis, we can define particular operators which we call orthogonal projections. So this is definitely a generalization of orthogonal projections like we have them in linear algebra. In fact, for infinite dimensional spaces, it will be a little bit more complicated. Moreover, we can also generalize matrices, so we will talk about linear operators on Hilbert spaces. And some special cases we have there are unitary operators and self-adjoint operators. And maybe at the end of the course we can also talk a little bit about the spectral theorem for these operators. Okay, there we have it. This is the overview of the course, and now we can start with the content. Which means we can immediately start with the core ingredient of a Hilbert space, which is an inner product. So what we get there is a so-called inner product space. And there I should know that we always consider real vector spaces or complex vector spaces. And since we don't have to distinguish both cases most of the time, we will just use the letter F. So it either stands for R or for C. So you can remember the field of scalars is always fixed with the letter F. Therefore our vector space is always an F vector space and we denote it by X. And now you know, throughout this video course here, X always carries an inner product denoted by these pointy brackets. So it's a map with two inputs, both coming from X. And the output is just a scalar. And now if you don't know it, such an inner product needs exactly three properties. So first, an inner product always has to be positive definite. Which means two things. On the one hand, if we put in the same vector x in both arguments, we get out a real number which is non-negative. And on the other hand, if this outcome is exactly 0, then we know the vector has to be the 0 vector in X. Okay, and now the second property tells us that we have linearity in the inner product. And you see, we will formulate it such that we have linearity in the second argument. And linearity means two things. First, we can pull out the addition from the second argument, and we can pull out a scalar from the second argument. So you should see, the first argument is always fixed with a vector y, and the things only happen in the second argument. And now finally, the third property tells us that we have almost linearity in the first argument as well. Simply because we want to have a kind of symmetry for the whole inner product. This means if you exchange both arguments here, you don't change much, you only add a complex conjugation. However, this is only for the case of a complex vector space. For the real case, we indeed don't change anything. So we have symmetry in the real case and the conjugate symmetry in the complex case. So this implies that in the complex case we don't have linearity in the first argument, but rather a conjugate linearity. So if we want to pull out a scalar from the first argument, it gets a complex conjugation in the end. So please keep that in mind. In the complex case, the first argument and the second argument behave differently. And therefore it's also possible to switch the definition so that you claim the linearity in the first argument. In fact, many mathematicians do that, but in this video series here, we will exclusively work with this definition here. Okay, so this is an inner product, and now we can finish our sentence here. A vector space with an inner product is called an inner product space. Indeed, some people call this a pre-Hilbert space because most of the stuff we need for a Hilbert space is already there. So a lot of properties we already have in a pre-Hilbert space. For example, the famous Cauchy-Schwarz Inequality. This one is such an important property that we should definitely talk a little bit about it here. So for any inner product space X, we have this inequality. So we take two vectors X and Y in the inner product and we look at the result in the absolute value squared. And this real number we can estimate by the inner product where just X is inside and with the inner product where just Y is inside. And by the properties of the inner product, we know that these two inner products are always non-negative real numbers as well. So the Cauchy-Schwarz inequality simply tells us the relation between this product and the inner product of X with Y. And the proof of this statement is not so complicated, and indeed you can find it in my functional analysis course and also another one in my abstract linear algebra course. But for the sake of completeness here, let's quickly write down one again. Now the case that y is the 0 vector is immediately clear, so let's consider the one where y is not the 0 vector. Because then we can look at the vector x minus a scalar times y. And let's choose this scalar as y with x divided by the inner product y with y. And this is exactly the scalar I want to have for the vector y here. And now let's take this linear combination here and let's put it into the inner product. And I want to put it in both arguments, which means we get a non-negative number out. So this is just using the fact that the inner product is positive definite. And now in the next step, obviously to simplify that, we want to use the linearity. So what we get out are exactly 4 terms in the sum. And the first one is x with x, and the second one is that element with x. Which means we have a minus sign and we pull out the scalar from the first argument. Hence, we have to add a complex conjugation for the scalar. Okay, and what remains here is simply the inner product y with x. And then for the third step, let's combine this x with this vector here. So again, a minus sign from the scalar, but no complex conjugation. And then, as I've already told you, we actually have x with the vector y. So please don't forget, the order matters in the inner product because we could have the complex case. And then finally, for the fourth term, we have to connect this vector with that vector here. So we pull out one scalar with the complex conjugation and the other one without it. And since we get 2 times the minus sign, we actually have a plus sign. And then what remains is the vector y with the vector y in the inner product. And with that we have it. We have all the 4 terms now. And now we want to simplify the terms, and you should immediately see that we can cancel this inner product here. But after this, you also see that this term is exactly that term. The only difference we see is the sign, so these also just cancel out. So in the end, only the 2 terms remain. The first term is already nice enough, but in the second one, we can use the third property of the inner product. So you see, the one inner product here is the complex conjugation of the other one, so we can put it together as the absolute value squared. In other words, this is just calculating with complex numbers. And we don't have to change the denominator here, because now we are finished. We have that this is greater or equal than 0, so we can bring this to the other side and multiply with the denominator. So we get the whole Cauchy-Schwarz inequality as before, and the whole proof is finished. And now I can show you that we can immediately apply Cauchy-Schwarz for showing that we also have a norm on our inner product space. In other words, the result is that with an inner product, we can also measure distances. You just take the inner product x with itself, and then you take the square root of that. And there we usually use the common norm notation, because it's actually a norm on our vector space X. Hence, all the 3 properties of a norm are satisfied here. More precisely, if we want to show the triangle inequality for this norm, we can use the Cauchy-Schwarz inequality. If you want to see the actual details there, you can check out my functional analysis course. Here it's good enough that we know that this norm is well defined, and then we can actually define Hilbert spaces now. So we take an inner product space and we call it a Hilbert space if it is also a Banach space, which simply means it's a complete space. So what we have is that X together with this new norm is a Banach space. And there we have it. Now you know what a Hilbert space is. And then I would say with the next videos we go deeper into the theory and we look at examples. So have a nice day and bye bye.